Boom, harmonic series. What the heck? So, you've all probably seen that great little proof of the harmonic series being a divergent series. The harmonic series, of course, being the sum over the reciprocals of the integers. And since we've all seen that original proof so many times where you group all the, next power of 2 number of terms and show that it's all greater than the sum of a bunch of 1/2s, yeah, classic proof. I'm going to avoid that one altogether, and I'm going to demonstrate 3 different proofs that I think are very interesting, that show that the harmonic series does diverge, all, of course, proof by contradictions, much like the first one, where you assume that it does converge, and then, well, no, I guess the first one isn't a proof by contradiction since you're showing that it's larger than an also infinite series, which, rip Infinite Series, I missed that show so much. In a couple of these cases, they will be proof by contradictions, perhaps another comparative proof like the classic one that everybody knows. And then I'm going to pose a question at the end of the video and then answer one half of it because it's very easy to answer, and the other half won't be very easy to answer, and I'll have to save it for another video. So let's do it. Naturally, there's nothing better to prove the infinitude of something than with my infinitely supportive friend, Trusty Cup of Joe. Always there by my side. Okay, so as we all know, the harmonic numbers are the nth harmonic number, usually denoted h sub n, is the nth term in this sequence of sums, which are the sums of the reciprocals of the integers. So 1 over 1 plus 1 over 2 plus 1 over 3 plus ... plus 1 over n. So this number is the nth harmonic number, and the harmonic series is simply that which goes forever. Right, so 1 over k, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus ... but it goes forever and doesn't stop. And we've all seen the classic proof where you group the groups of 2 and then 4 and then 8 and then 16 terms together, show that they're all, when you add those up, greater than 1/2, and that this ends up being bigger than a sum of 1 and then a bunch of 1/2s. So you can show that this is greater than 1 plus 1/2 times k for any integer k. So because this k can be as large as you want, this can be as large as you want, which makes this as large as you want, which means that this does go to infinity. I won't say it equals infinity, even though I just did. Deal with it. But I'm not going to do this proof today because we've all seen that. Not very interesting. I'm going to show 3 completely separate proofs that demonstrate the infinitude of this series. So this first one is a proof by contradiction. We're going to assume that this does in fact equal a finite sum, h. We'll just call it h. All that this sum comes down to is proving that this number is greater than itself, right? So since h is what we're saying is, where h is obviously a real number, right, we're going to prove that this real number h is greater than itself, which is a contradiction because no number is greater than itself. So the assumption is that this does equal this number, and all we're going to do is say that this is equal to 1/2 plus 1/2 plus 1/2. So essentially taking this 1 and breaking it into 2 1/2s. I hope that's clear. And then this is, the 1/3 plus the 1/4 plus the 1/5 plus the 1/6 plus etc., forever and ever. So all I did was take this first term, 1, and break it into 1/2 plus 1/2, because that's what it's equal to. So now all I did, this first step, was just to break this 1 into 1/2 plus 1/2. That's all I needed to do. And so now, the next step is where the contradiction comes in. This is greater than, and at first the first few terms are going to be the same, but I'm going to group them as such. And now this is where they start getting unequal, because 1/3 is more than 1/4, which means the sum of 1/3 and 1/4 has to be greater than the sum of 1/4 and 1/4. So it's strictly greater than 1/4 plus 1/4. Naturally, 1/5 is more than 1/6, so the sum of these two terms has to be more than the sum of 1/6 and 1/6. So it's greater than 1/6 plus 1/6, and that will carry on forever, right? If you have 1 over n plus 1 over n plus 1, that sum will be greater than just 1 over n plus 1 plus 1 over n plus 1. But now look what we can do. We can say that this is equal to 1/2 plus, what's 1/2 plus 1/2? That's 1. 1/4 plus 1/4 is 1/2. 1/6 plus 1/6 is 1/3. And as you can see, we're just going to end up with the harmonic series again, except plus 1/2. So this right here is h plus 1/2. So what we've just been able to prove is that h is more than itself plus 1/2, which doesn't make any sense. So what I stated at the beginning was slightly incorrect. I wasn't going to show that h is bigger than itself. I've something even sillier. I'm showing that it is bigger than a number that is bigger than it. Right? Anything plus 1/2 is going to get larger if it's a real number. So a number can't be more than itself plus 1/2. Right? So that's the contradiction. So contradiction, right? Two arrows pointing at each other. Contradiction. Right? Contradiction. That's not possible. You cannot have a real number that is greater than itself plus 1/2. And so there's proof number one, that the sum of the reciprocals of all the integers is an infinite quantity. It gets as large as you want, and you will eventually reach any number, though incredibly, incredibly slowly, because it does grow logarithmically, which is what we're going to need to know in the next video, the fact that it does in fact grow logarithmically. So I hope that was clear, right? We showed that a real number, if it exists, is great. This sum, as a real number, it is greater than itself plus 1/2, which is not possible. Therefore, this is not equality, and this sum does not converge to a specific value. Next proof. The next proof that I have of this fact is actually the one that I said that I was going to do, where I prove that it's bigger than itself, and it comes from this fantastic book by Julian Havel right here that I've been talking about, and from which many things are going to come later on in this channel. And simply, we're again going to assume that this sum, this infinite sum of terms equals some constant h, and that's 1 over 1 plus 1 over 2 plus 1 over 3 plus ... This is actually quite a simple little proof. We can sort of exchange all of these fractions for equivalent fractions by multiplying the tops and bottoms by 2. So we get 2 over 2 plus 2 over 4 plus 2 over 6 plus ... forever and ever. This is of course equal to 1/2 plus 1/2 plus 1/4 plus 1 over 4 plus 1 over 6 plus 1 over 6 plus ... which is of course less than 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus forever and ever, which is of course the sum that we started with, h. And so instead of showing that it was greater than itself plus 1/2, we actually showed that it's less than itself, which is also a contradiction. Right? So this is, again, another proof that the sum of the harmonic numbers, or the limit of the harmonic numbers as a sequence, is infinite and therefore does not converge to a finite sum h. Third proof. The third proof is an exceptionally lovely proof using integral calculus. So what we're going to do is we're going to consider the integral from -infinity to 0 of the very cool looking function e to the x over 1 minus e to the x dx. And we're simply going to rewrite this as the integral from -infinity to 0 of e to the x times 1 over 1 minus e to the x dx. Naturally, if you know much about exponential functions, the regular old e to the x function from -infinity to 0 is between, so here I'll just write it out, so e to the x is between 0 and 1 in this fashion when x is between -infinity and 0, which means over this interval, this quantity is between 0 and 1, which means we can use the geometric series to evaluate this. So we can rewrite this as the integral from -infinity to 0 of e to the x times the geometric series represented here, so it's e to the x to the 0, which is 1, plus e to the x to the 1, which is that, plus e to the 2x, plus e to the 3x, plus ... the geometric series, right? And we can evaluate this term-wise. So what we end up with is, of course, the integral from -infinity to 0 of the sum from k equals 1 to infinity of e to the kx, right? Because multiplying this e to the x in is going to increase the power of all of these by x, right? We're going to get e to the x plus e to the 2x plus e to the 3x plus e to the 4x, and everything's going to go up by 1 dx. And so what we can do, because this converges absolutely, and the sum converges absolutely, and the integral converges absolutely, we can just swap those two things. And so we end up with the sum from k equals 1 to infinity of the integral from negative infinity to 0 of e to the kx dx, right? And naturally we can do basic anti-differentiation here, so we get the sum from k equals 1 to infinity of the formula 1 over k times e to the kx, evaluated from negative infinity to 0. Naturally, when we plug in the upper bound of 0, we end up with the sum, the harmonic series that we're looking for, so we get 1 over 1 plus 1 over 2 plus dot dot dot, and then when we plug in negative infinity to this, e to the negative infinity, or the limit as the bound approaches negative infinity, is going to go to 0. So we do end up with just the harmonic sum. Of course, this does not prove that this sum is infinite. What we need to do is we need to evaluate this integral in a slightly different way. So we've shown that this integral is equal to the harmonic sum, right? So we can call this h for now, right? It may or may not be infinite, but what we're going to do is prove that now by evaluating this integral in a different way. So we've shown that it's equivalent to the harmonic series by simply plugging in these bounds into this term here. So if you plug in 0, you get 1 over k. If you plug in negative infinity, you get 0. So this ends up being a sum over all of the reciprocal integers. So now we just need to evaluate this bound, this integral in a different way, and that will show us that this is infinite. So this integral is actually really, really easy to solve, right? Because we can use a simple u substitution, because it appears that we have the derivative of the denominator in the numerator. So all we have to do is say u is equal to 1 minus e to the x, which implies that du is equal to negative e to the x dx, or negative du is equal to e to the x dx. We have e to the x dx right there. And now this integral will run from, what happens when I plug in negative infinity into x here? I get 1 minus 0, so it starts at 1. And what happens when I plug in 0? I get 1, so it goes from 1 to 0. That negative comes out the front, and we end up with du over u. This is very easily integrated by using the natural logarithm, so we end up with the natural logarithm of the absolute value of u from 1 to 0. Using the negative, we can flip the bounds, but essentially what you end up with is the negative natural logarithm of 0 plus the logarithm at 1. The natural logarithm at 1 is 0, and the natural logarithm at 0 is negative infinity, and negative infinity is positive infinity, which shows that the evaluation that we had before, which was equivalent to the harmonic series, turns out to be an infinite quantity, like we've shown before. So there's 3 proofs that the harmonic series is in fact infinite. There is no finite sum that this sequence tends to. So that's 3 different beautiful proofs, 2 of which came from this book right here, because I'd like to start going through this book. And what I'd like to do is pose an interesting question to you, because we can break this sum up into pieces if we wanted to. We could break it up into a finite piece, which means what's left over has to be infinite, or we can break it up in ways that aren't exactly, clear whether they're infinite or not. What I would like to propose is that we break it up into 3 different pieces. We're going to take 1 and set it aside. So there's 1 over 1. Obviously that equals 1 and is not infinite. So taking away just one single term from the series does not change the size of the series. It is still infinitely large. And the next one we're going to call C. And this will represent the sum of 1 over 4 plus 1 over 6 plus 1 over 8 plus 1 over 9 plus 1 over 10, plus etc., etc. The sum of the reciprocals of all the composite numbers, which means I'm sure you can see where this is going. We're going to define another series, P, which is 1 over 2, plus 1 over 3, plus 1 over 5, plus 1 over 7, plus 1 over 11, ... Now, because the harmonic series is infinitely large, and this little term right here is 1, and not infinitely large, then it must be the case that at least one of these sub-series, I guess you could call them, of the harmonic series is infinite. And it's very easy to see that the composite one has to be infinite, because what does this contain? It at the very least contains every multiple of 4 as a denominator. And what is the sum of all those multiples of 4? Well, if we have 1 over 4 plus 1 over 8 plus 1 over 12 plus ... You could just factor out 1/4 from all of those things, and you end up with 1/4 times the harmonic series again, right? So because this contains 1/4 of this already infinite series that we know, then this one itself must be infinitely large as well. But that is not nearly enough to prove that the reciprocals of the prime numbers diverge. This was very, very easy, and proving that this one diverges is all you need to show that the whole thing is divergent. Of course, we're using the fact that it already diverges to prove that the composite one is divergent, but because this one is infinite, that does not mean that this necessarily has to be, right? Because as soon as one of the parts of it is infinite, then the whole sum is infinite, and it need not be the case that this is. As it turns out, this one, the sum of reciprocals of prime numbers, does in fact diverge as well. Now, because prime numbers are a bit more wily, I'll say, than composite numbers, this is a much more difficult proof to do, to show that this diverges. But what does that mean? That means that because this diverges, it has to have an infinite number of terms, which would then prove that there are infinitely many prime numbers, without mentioning anything from Euclid. And so, in the next video of this series, I'd like to show the proof that the sum of the reciprocals of the prime numbers does in fact diverge, thus showing that there are in fact infinitely many prime numbers. In a roundabout sense, it's sort of like killing a mosquito with a nuclear bomb. And so that's what we're going to be doing in the next video. Thank you very much for watching. I've got many, many other cool relationships for the harmonic series and Euler's constant and logarithms to go over, because this book that I've mentioned is absolutely phenomenal, and I cannot wait to share more of the stuff inside of it with you. So thank you for watching this video. This is infinite. This will be shown to be infinite. For now, we don't know, unless you know the proof already, in case piss off. And this is just one, so not infinite. Cool. So stay tuned for the next video. I have an Instagram page for the channel. It is at whatthehectagon, of course, spelled correctly, unlike my email, right? Hectagon, I spelled in the email with an A here, when in fact it's an O. Whatthehectagon on Instagram, so this is Instagram. I post channel updates there. I also am doing a lot more reading than I used to now, so I'm posting books that I'm reading that I recommend to people. I have a collection of vinyl records that I like to share. Follow me at whatthehectagon on Instagram. I'd like to point out that one of my best friends, who is very much into Dungeons & Dragons, has a YouTube channel called Marching West. He does like a little podcast about Dungeons & Dragons. He does Dungeons & Dragons all the time through his Discord server. He's very, very into it, and I'm sure he would appreciate a bit of a mention. So if you're into Dungeons & Dragons, visit his YouTube channel, Marching West. He also has an Instagram account, again, at Marching West. Also, this fellow, Bill, and I are starting another YouTube channel. I guess you could call it personal reasons, even though it's just kind of funny. Is called Fredwood Live. On YouTube, we're just called Fredwood. It's an amalgamation of two different things that were sort of important to us in our college days, which are getting farther and farther behind us. So this is, again, YouTube. We have a channel called Fredwood. We're going to do kind of silly, just us riffing off of each other vlogs that we edit together in humorous ways. But we're also going to start doing weekly video game streams on Mixer. And on Mixer, our name is Fredwood Live. So if you want to see two kind of dopey former college students do kind of ridiculous video game streams and also other things that we're going to do on top of that on Mixer, our username is Fredwood Live, so check us out. Likewise, we have a Twitter account to promote it, also at Fredwood Live. So I apologize for all of these different promotions. I figured I'd just start putting these out there. So there's a few that I'd like you to check out if you're interested. Is my Instagram account, whatthehectagon. On YouTube, my buddy Bill's channel, Marching West. It has to do with podcasts and the like relating to Dungeons & Dragons. The Instagram account for channel updates for that channel. Our joint channel, Fredwood, where we're going to be posting stream clips and vlogs that we make, which are not in any way intended to be serious. It's all supposed to be just kind of humorous. We're going to stream on Mixer, because that's the only way that we can use the camera that we have on my Xbox One, and we're not about to buy a Kinect to do on Twitch. So Mixer, Fredwood Live, and the Twitter account for that is at Fredwood Live. So if you're interested in any of these things, please give us a follow. I really appreciate it.